So this is cloud recording. I think all of you will have to hit continue here. Hi everyone, I'm Anurag Pandey. I'm a professor of civil engineering here at Cal Poly San Luis Obispo. And what we are doing here is that I have three of my brilliant students here with me. And what we are trying to do is go over the FE exam material that relates to engineering economics and traffic and transportation engineering. And my plan is to go over the FE review manual here and talk about what all is there, and then try to work out some problems as we go along. And what we'll try to do is maybe take a break in about half an hour, maybe take a 5-minute break in half an hour, and then reconvene. So without further ado, I will just go ahead and get started with the material. So hopefully you guys can see the document camera that I have created here. And on that document camera, what you're seeing is page 164 of the FE Civil Engineering exam manual that you'll have access to during the exam. And as you can see, the half of the page is water resources formula, and then you start with the transportation formula. And in transportation engineering curriculum, the way it's designed is that it has sort of three distinct aspects to it. And those three aspects relate with design, they relate with planning, and then operations. So there is material from all three of the aspects in the FE exam, from planning, design, and operations. And what I'll try to do is, as I'm going through these formulas, I'll try to point out if some of these formulas relate to planning, design, so that if you want to review further materials on it, you can go back and check the relevant material from your transportation engineering courses. Most of this material is covered under the introductory transportation class at most places. At Cal Poly, we cover it. Most of it is in CE 321. And right off the bat, I will come out and say that, that the pavement materials is not my strong suit. I will talk about that briefly here as we are going through the material. And then we'll try to work out some problems at the tail end of these types of tutorials. But again, I want to make sure that you understand that this is not something that I do research in and day out. So that's something that is not my strongest suit. But anyway, so we'll go over these formulas, and obviously in the exam, you will have access to this. So you're not supposed to know any of the other formulas, but I think it's good to know the conceptual ideas behind these formulas, because there would be some conceptual questions, is my understanding. Plus, it will be much easier to apply these formulas if you know what you're doing, because there might be some tricks involved in solving the problems. So first thing right off the bat, as you're reviewing these formulas, please remember, pay attention to the units. The units are very important. Just to give you a quick example here, if you look at the units for small v, look at this here. The small v represents vehicle approach speed. So it is a speed of value. And also capital V represents speed values as well. But if you notice, what's the difference between the two? Capital V is typically the design speed measured in miles per hour. But you will notice that the small v represents vehicle approach speed, that is in feet per second. So there are obviously these kind of things all over the place. So you have to be careful about, as you apply the formulas, that you're aware of those things. Okay? And let's look at some of the other formulas. Then you have the first formula in there that relates with design. So you will look at the intersection design portion of your class if you want to go details in this formula. This basically is talking about, this formula is talking about the yellow interval. How do you define the yellow interval? How long should the yellow light be at an intersection? And that depends on T, small t. Again, you'll look up what small t stands for. Small t stands for right here, driver reaction time in seconds. So you got this driver reaction time. Typically, this value would be given to you in the problem. The small v is the approach speed. Remember, this is approach speed, so it has to be entered in feet per second. 2 small a, and you can look at small a. Small a is the deceleration rate that the vehicles are able to generate as they are facing a situation where they have to brake. And then 64.4 is just a number that is basically accounting for the gravitational acceleration constant. And then capital G is the percentage grade divided by 100. So uphill grade will be entered as a positive number, the downhill grade entered as a negative number. And so you will just, so G value, if it's, you're talking about 5% upgrade, just to take an example, then you will enter G as 5 divided by 100, so 0.05. Okay, because you can see percentage grade divided by 100. Okay, so 5% upgrade will be entered at 0.05, and then you can solve the problem based on that. And then this R is the red interval. Okay, so the red interval is how much should be the all red interval. So here, one thing about the intersection safety to keep in mind is that anytime you're designing an intersection traffic signal timing, you need to make sure that for maybe a second or a 2-second period, depending upon what value you get out of this formula, you have all approaches to be red at end of any phasing. So for example, if the signal is turning from green to yellow to red, when the signal turns red, the next approach does not turn green until after a certain time period that we call the all red interval. And this formula, the second formula, this is providing you with small r w plus L over V. And you could see the W is the width of the intersection curve to curve. L is the length of the intersection, length of vehicle that is crossing the intersection. It could be a design vehicle. If you have expecting a lot of trucks, then that value could be larger. But if you're just using cars, then that length would be about 20 feet. And then this V is again about approach speed. And R, small r, the value you get out of this formula is the length of red clearance interval. That is the all red interval that we were talking about. Now, one thing that you might be thinking about that, hey, when I designed the yellow interval, I had to account for the grade value. What if the intersection is also at a grade? Now, this is a good question, but why are we not taking into account the grade value here? Is that first of all, the intersection width would be much smaller than the approach width or approach length that you're talking about. The yellow interval has to account for that the vehicle is farther away from intersection. So you're talking about a larger distance where the grade starts to make a lot of difference. And because the red width interval or red interval is just dependent upon the intersection width, that is much smaller value. So you are okay with just using the width and the design speed as your value, and you don't have to account for vehicle accelerating or decelerating and so forth. You can assume that they are able to travel through design speed and they're not actually accelerating or decelerating. Okay, and so again, this vehicle change interval formula designs or relates specifically with intersection design. The next set of formula is stopping sight distance. This relates with design distances at any given location on the roadway. So anytime you have a roadway location, could be intersection, not intersection, middle of the highway, middle of a 2-lane road, whatever, you always want to allow for stopping sight distance. And this formula provides you with the required SSD. How much distance do you actually require? And again, if you pay attention to the formula, this has 1.47 value. This 1.47 is there because the V now is capital V. And as I told you before, that relates with design speed that is entered directly in miles per hour. If you want to learn where this 1.47 is coming from, just to make it clear, it is coming from this factor 50 to 80 divided by 3600. Right? And where does that 50 to 80 divided by 3600 comes from? 50 to 80 is basically a feet to mile conversion or miles to feet conversion. And this 3600 is hours to second conversion. Okay? So this 1.47 factor is there so that you can enter the capital V value here directly in miles per hour. Capital V again is in miles per hour. 30 is again a factor that accounts for all of that. And then A divided by 32.2 is what we call the friction factor. And remember, A is, and it's a dimensionless unit, okay? In this case, F is friction factor. And A divided by 32.2 is the longitudinal friction factor. And so I will just want to make sure that I'll just note that it's an FL. Okay, so when you're moving forward, when your vehicle is moving forward, what happens to how much friction factor you're able to generate? Small a is again the deceleration rate that you're able to generate, right here, feet per second square, and you divide by 32.2, which is the gravitational acceleration constant. Now, in a lot of problems, you will not need to worry about the friction factor, the longitudinal friction factor here. But it's helpful to know, because in some problems that might be the actually the given value, and because it does not appear in this formula, you might have to account for that fact. Okay, and then this G is the same thing. You do the plus sign if it's an uphill, you do the minus sign if it's downhill. And what you're trying to ascertain is how much distance would you need if you're traveling at a certain speed, let's say 60 miles per hour. How much distance you would require to actually come to a complete stop. Okay. So you can see that if this value is positive, what happens? If this value is positive, this value as a whole, this denominator will increase. That means this second value as a whole will go down. Okay, and then your SSD required will go down. So obviously on uphill, it's easier to stop, so you don't need as much distance. And if it's a negative value, this denominator will go smaller. That means this value as a whole will go up. That means you'll require more stopping distance to stop. Okay, so that's the general idea of this formula as you're trying to stop or estimate the stopping side distance. Okay. What I'm going to do is I'm just going to go over here, and I will just wait for a confirmation if there is any questions about any of these things that we have talked about just here. So I will just give my students some opportunity to ask questions at this point. And yes, please go ahead. And if there are no questions, go ahead and say no questions.
No questions.
Okay, perfect. Thank you. So that's the kind of validation I'm looking for. Okay. So what I'm going to do is next is we're going to go over to the next page of the manual. And next page of the manual is, again, just all about the design and all about transportation. And again, what I'm going to do is I'm going to not talk about what's on the top here, because that is talking about the traffic flow relationship. So that goes into traffic operations. Traffic operations. So we'll talk about that in a little bit, but let's first cover over all the design aspects of things. Okay. I hope it's a little bit trying to become unclear, but what I would recommend is that when you are viewing these lectures, what would be helpful is that you have these pages, page 165 of your civil engineering exam manual open, so that you can take notes, and even if some things are not clear on the document camera here, you are in fact able to see those things clearly and make notes and so forth. So, and then there is, again, the design aspects comes in again on vertical curves, side distance related to curve length. And then, so you get the side distance related to crest vertical curve, and then you have the sag vertical curve. And then what happens, and again, we are trying to figure out if you are in a vertical curve situation, what happens when you're trying to figure out the side distance issues. But before we talk about the side distance issues, let's talk first about what those curves even look like. And again, there is formula related to horizontal curves here as well. And how do you essentially account for all those things? But before we learn all of that, what we need to learn is the fundamentals of these ideas. And for that, we need to kind of skip over and look at horizontal and vertical curve discussions, and which goes over to the next page. And again, this again relates with, generally speaking, it relates with highway design. Okay, again relates with highway design. And then this is page number 166 of your FE exam manual. Now this is the horizontal curve formula. So if you look at the top of the page, these are horizontal curve formulas, and understanding these formulas is very critical before you can understand all that side distance stuff that came before. Again, if you are referring to this, and if you want to go back to your courses or course notes, the highway design portion of your course notes is what you will refer to. Now, if you're talking about the horizontal curve design is always based on top view or a bird's eye view. So what you're looking at is the bird's eye view of a horizontal curve. And horizontal curves are provided so that you have a smooth change in direction. Remember, I'm saying smooth change in direction. Now, if you think about what does smooth change in direction means, what it means is that sometimes the change in direction is not smooth, right? You talk about your intersection. So sometimes when the road turns, you arrive at an intersection and then you make a complete stop and make a right or left turn, right? But in some cases, when you want to provide for higher speeds, you don't want to have vehicles to stop, okay? So then the change in direction is achieved using horizontal curves, where the curves, basically the vehicles can make smooth transition between going from one direction over to the other. So this is a typical horizontal curve. In a typical horizontal curve, what you have is an initial tangent. So basically, this is your initial direction of travel. So this is your initial tangent, your initial direction of travel. And then when you move along, this is your final direction of travel. Okay. Now, how do you achieve transition between them? Now, obviously, one way to achieve transition is basically you continue this tangent all the way, and then you continue this tangent all the way, and basically force the vehicles to make a turn here. Make a almost, maybe even more than a 90-degree turn here. What does that mean? That means the vehicles will have to almost come to a stop or a very, very slow down speed and then make that turn. So obviously you can make this turn as sharp as smooth. So the sharpest possible turn for this curve would be you force the vehicles to come all the way over here and then make the turn. A smooth turn would be you provide this radius to be as large as possible. So you provide, so obviously there could be many, many ways to provide this turn. You could have had the vehicles turning here. You could have vehicle turning here, vehicle turning here. So what this curve shows here, that's drawn already on your manual, one example of how do you provide transition. And what they're using this curve for is to give you an idea about different metrics, different geometric design metrics of this curve. Okay? Again, this is just one of the options, the way you could have connected the initial direction of travel to the final direction of travel. So you can see here that this is the center of this curve. Okay, so this is the center line of this curve. And this design is typically a circular curve. Okay, when you're designing the horizontal curve, it is a circular curve, and a lot of geometric features flow from that, or follow from that. So if this is a circular arc, you could figure out a lot of different things from this. Okay, what are some of the things that we can figure from this? That what you can figure out from this is, again, this is horizontal curve. So you will see that this is the PC. This point is called the PC, point of curvature. This is where the curve begins. This is the point of tangency. This is where the curve ends. And basically a straight line starts after that. And there is a straight line before that and a straight line after that. And the middle portion of these are curves. Okay. Now, there is a concept of design that's beyond the purview, is that sometimes you might have to provide transition between a straight line and the curve, but we are not going to talk about that here because that's beyond the scope of that this design. That may be applicable for the licensing exam, for the professional engineering exam, but this is not applicable here. So we're going to stick with the fact that you don't provide any transition. This at point PC, you are at a straight line, and then right from the get-go, you start with a circular curve. Okay, so that's the kind of transition we're talking about. If the curve is too steep to go from straight to a very small radius, then you might have to talk about transition and so forth, which we're not going to go over here. So let's go over and talk about what all of these things are. So first of all, if you measure the straight line distance between PC and PT, this distance is called the chord length. Okay, it's called LC. This is the straight line distance between PC and PT. The length of the curve is defined as this arc length. Okay? And this arc length will obviously be based on how do you measure the perimeter of the circle. Obviously, this is not the full circle. This length of the curve will be dependent upon how much angle you are subtending on the center. And this angle by geometry will be the same angle as over here. So this angle and then this angle are the same exact angles. Okay? And you can deduce that from geometry because you know that the angle between tangent and the angle between the tangent as well as the radius is 90 degrees. So you could figure out that this from here to here is a radius, from here to here is also a radius. So these two lengths are the radius, and then these two lengths are the tangent. So this angle is 90 degrees, and you can deduce a lot of things from that. So one of the things that you can deduce is that T is equal to R tangent delta over 2. So whenever I studied this thing, we used to call this I angle to be delta. So see, you can see that here, also called delta. So this is something important because if you're referring between your course notes and your and the FE exam manual, it's important to remember they call it I here, but it's the same thing as delta. That in your class notes, most professors will probably mention it as delta. So don't get confused by that here. And you can see because of symmetry, this portion will be I over 2. So you could see that here, this angle is I over 2, and then this angle is also I over 2. And because I told you that this angle is 90 degrees, you can derive this formula. T is equal to R tan delta over 2 or R tangent I over 2. But if you want to derive that same thing from this length, this is LC over 2. This length over here is LC over 2. And then based on that, you could derive LC over 2. Cosine I over 2 will also give you the tangent length. Okay, so you could derive this tangent length using this formula as well. Now, and then this is the external distance. This is going to be the external distance E. The formula for E, how it relates with E is right here. R over E plus R is equal to cosine delta over 2. And again, all of these you can derive from geometry. So I'm not going to go into all the derivation here, but you need to remember what each of these terms actually mean. And then M is middle ordinate. Okay. Now this is an important, very important formula of M, because think about how this is all going to come back to your design distance. Okay, how this is going to come to your design distance is that, think about this. If you have drivers traveling in their vehicles going this way, they're trying to turn from here. As they approach this PC point, they need to be able to see around the bend what's going on. If there is some object here that might cause some problems to them. Okay, so it's very important for the drivers as they approach this point on the curve to be able to see around the bend over here to see if there is any potential problem. Now, this M distance is something that the agencies, the Caltrans, for example, might want to make sure that this is clearer, because if there is, let's say, if there is a site obstruction over here, let's assume that there is a site obstruction, let's say at this point. Okay, if there is a site obstruction at this point, this is the last point you will be able to see, right? But let's say if the site obstruction is moved up to another point, let's say if there is a site obstruction where the text M stands, okay? If this is where the site obstruction is, now you think about this, now your car has to be almost at this point to be able to see around the bend over here. You see? So as the site obstruction moves closer and closer to the curve, your vehicle has to come way further up to be able to see what's around the bend. So what this does is that if you have shorter and shorter clearance distance on the median, and this M distance to the obstruction goes down and down and down, as your obstruction moves forward, your available site distance goes down. What's the implication of that? The implication of that is that as this obstruction moves forward, if the obstruction, like if there is a tree or if there is a side of a building, whatever it might be, as your obstruction moves closer and closer to the roadway width, you need to provide, you are only able to provide a smaller design space, because your vehicle has to be able to react what's around the bend, and you're not able to see as much distance around the bend as your obstruction moves closer. So this M formula, M equal to R minus 1 minus cosine I over 2, is a very important formula, because if you know where the obstruction is relative to that, you can figure out what the radius has to be. And then that radius has implications for how much speed you can provide on this curve. Okay? So those things are very, very important and have to be kept in mind. So that's the implication of why we want to learn all these formulas, is that because this formula relates with how fast you drivers will be able to go on that curve, because this will have an impact based on where the obstruction lies. And then if you go back to that formula, you will see. And then there are some other things here. How do radius and degree of curvature relate with each other? For this, you have to be, so you can always relate because sometimes the curve will be specified to you in the form of radius, and in some cases it will be defined in terms of degree of curvature. Okay? So if you think about the radius and how does that relate to degree of curvature, it's the degree of curvature D is length of arc or degree of curvature is defined as 5729 over 0.58 over D, and it is based on this 100 feet length of curve. Okay, so so degree of curvature is what would have been the angle if you just take 100 feet arc of this curve, which they do here. So this arc is 100 feet, and it's obviously not drawn to scale, but this arc is 100 feet. So if you kind of subtend it back, what angle does it create on the center line? Okay, so that's how you create the D. Its degree of curvature is defined as the angle that is subtended of length of arc 100 feet. So I should say D is angle for length of arc of 100 feet. So if you take the length of arc of 100 feet, how much angle do you get there? And this 52.7, you can derive this formula by saying, okay, if the angle was 360 degrees, then your arc length would be 2 pi r. So then you are figuring out what will be the angle if your arc length is 100 feet. Okay, so if you solve that and account for that, this is where you'll end up here, and where you take the value of pi to be. So this would be, this question mark will be in this case D. So if you simplify that formula, you could do that on your own time. You could get the value for R, and then this is how you'll get this formula. Okay, and then there are some other things here that you could derive using geometry here. The small c value, small c is the length of the subchord. You could derive small c is basically length of any subchord. So you could basically, if you are not considering the whole curve, you're considering just a small portion of the curve. C is 2r sine small d over 2, and then basically they're just taking any given value, any given point on the curve. You can derive that, because sometimes they will be asking you what is the length of the curve only up to this point. Okay, and then this is small l. Small l is curve length for the subchord. So small l is not the length of the whole curve, but only up until a certain subchord. So this is obviously based on d here. So r times d divided times pi over 180 degrees. And then this e is called the external distance. External distance, you could derive this as well. That's basically just the difference between from this point onward, and you subtract this radius from it. And then this is what you'll get, the external distance. So here are some things some types of things that you will worry about. Is that one question that gets asked a whole lot is the question of stationing. Okay, so station in US customary units is measured as 100 feet. Okay, so sometimes you will get asked the question about stationing. So one station is equal to 100 feet of distance. Now, how do you define stationing here? Okay, so your stationing is always sort of, whenever you're doing design problems, it's always defined from left to right. And let's say if you're given the stationing of PC, Right? So you are given some stationing of PC is, so stationing will typically be given to you. Let's say the station is given to you, a certain station is given to you. So what you'll do is, and then they ask you the stationing of PI. PI is the point of intersection. PT is the point of tangency. That's where the curve ends. And PI is the point where the tangent would have met. Now, if you want to find the stationing of PI, what you do is like you take the stationing of PC and then you add the tangent length to it. Okay? You add the tangent length to it, and then you'll get the stationing of PI. And it'll be clearer when we do example problems. But if they ask you stationing of PT, you don't design it or you don't figure it out from stationing of PI. Your station of PT, so I'll just write down the formulas here. That should be helpful to you. So station of PI is equal to station of PC, and you add to that plus T. Okay, tangent length. And obviously you're going to do that in the stationing units because T is 100 feet, or T is going to be in feet, and you divide that by 100 to get the stationing. So you will make sure that you're adding it consistently. We'll make it clear when we do some example problems. But if you ask for stationing of PT, is going to be also defined in terms of stationing of PC. So the reference point still station of PC. That's the key point. But plus the arc length. Okay? If you're trying to go for stationing of PT, you'll define the full arc length. But if you're trying to get the stationing of any given generic point on the curve, you'll add the arc length up to that point. Okay? So that's basically one key thing that you get asked for. And I've seen students kind of make a mistake in my 321 class, is that sometimes when the station of PT gets asked, they'll try to define it based on stationing of PI, which is incorrect. You have to define all the stationing in the form of reference point of PC. And then you add the curve length in this case, because you're looking at the top view and your roadway length is basically, your horizontal plane basically is defined by that horizontal curve arc. Okay? So these are some things that will be useful for us to solve problems on horizontal curve design. So I will just take a few, just quick break and ask you guys if there are any questions about this.
There are no questions, but we might actually want to end the meeting real quick so that the video can download, just to make sure it all looks correct. So
Okay.
just in case we only lose half an hour instead of 2.
Okay, so that makes perfect sense. So what I'll do is I will just pause the recording and maybe not end the meeting, and then maybe we restart recording after that, and I'll take a look at the cloud recording in the meantime. I'll just go ahead and pause the recording, maybe not end the meeting because I have a good setup going right now.
Okay, if you can view the recorded video while staying on the meeting, that'll work.
Yes.